It sat in silence for more than 100 years, a cracked clay tablet buried in the sands of ancient Babylon, overlooked by history itself. To most eyes, it was nothing more than a relic, another broken piece from a world long gone. Archaeologists brushed the dust from its surface, noted its wedge-shaped cuneiform markings, and placed it among countless other finds. No gold, no carvings, no images of kings or gods, just numbers etched into hardened clay. For decades it was dismissed as dull, a record of food rations or temple goods. Even when it was catalogued at Columbia University under the dry name Plimpton 322, it raised little interest. Generations of scholars walked past it, unaware of the hidden truth resting quietly inside. Yet the tablet seemed to wait, holding its secret through wars, shifting empires, and forgotten archives. Only with the rise of modern technology, when artificial intelligence finally examined its patterns, did the silence break. What the tablet revealed was not myth nor a simple record, but something that shook the foundation of history. It was mathematics of breathtaking precision, carved nearly 4,000 years ago. Knowledge that should not have existed in that age. A voice from the past, finally speaking, asking us to question everything we thought we knew about human history. Found in Babylon in the early 1900s, deep in the hot, dusty ruins of southern Iraq, an American archaeologist named Edgar J. Banks made a discovery that would later echo across history. Banks wasn't just a scholar. He was a man of many talents, adventurer, antiquities dealer, and even diplomat. His daring expeditions and colorful life would eventually inspire the creation of the famous fictional hero, Indiana Jones. But on that day, he wasn't chasing treasure or golden idols. Instead, his eyes fell on something far less impressive at first glance: a small, broken slab of baked clay. The piece was chipped at the corners, no larger than a paperback book, and covered in tiny wedge-shaped marks known as cuneiform. Unlike the grand statues or decorated walls of Babylon, this tablet held no carvings, no artistic beauty, and no clear sign of wealth. To most, it looked plain, almost worthless. Yet hidden within those neat rows of symbols was something extraordinary, though Banks himself didn't realize it. He sold it for a few dollars to George Arthur Plimpton, a wealthy collector who valued education and history. In Plimpton's collection, the tablet was quietly labeled Plimpton 322. At the time, no one knew this clay fragment would later challenge our entire timeline of mathematics. It began here, in the dust of Babylon, waiting patiently for its story to be heard. A small clay slab at first sight, the tablet hardly seemed special. Roughly the size of a small book, its corners were broken, its surface uneven, and its color the dull brown of baked clay. There were no symbols of kings, no carvings of battles, no religious inscriptions to catch the eye. Instead, its surface was filled with rows of tiny wedge-shaped marks, pressed carefully into the clay thousands of years ago. These marks, known as cuneiform, were the writing system of the Babylonians. To most archaeologists of the time, such tablets were common, often nothing more than records of grain rations, trade lists, or simple temple inventories. And so, this particular slab was filed away, its true meaning left unnoticed. Yet even in its simplicity, the layout looked deliberate. The 4 neat columns and 15 rows seemed too structured to be random. The numbers carved into it weren't scattered or chaotic. They carried a sense of hidden order. Still, without context, the clay slab told no clear story. For nearly a century, it rested in silence, overlooked as a dull piece of bookkeeping. Only later would experts realize that this plain object, this unremarkable tablet, was in fact a coded time capsule of mathematical genius. What looked like scratches in clay would turn out to be a message across the ages, one that could rewrite the history of human knowledge. Into Plimpton's hands after Edgar J. Banks uncovered the clay slab, he didn't treat it as a priceless treasure. To him, it was simply one of many artifacts he had collected during his expeditions. For only a few dollars, he sold it to George Arthur Plimpton, a wealthy New York publisher and collector of rare books and educational materials. Plimpton was fascinated by objects that reflected humanity's long pursuit of knowledge, and the small Babylonian tablet fit neatly into his growing collection. Once purchased, it was carefully placed among manuscripts, scrolls, and other ancient items. Eventually, Plimpton donated his collection to Columbia University, ensuring its preservation for future generations. The artifact was given a dry catalog name, Plimpton 322, with no hint of the extraordinary secret it carried. For decades, it sat quietly on a shelf, treated as little more than a curiosity from a distant past. Scholars who glanced at it assumed it was routine, perhaps a ledger of rations, lists of goods, or temple offerings. Nothing about its plain appearance suggested that it contained one of the greatest mathematical revelations in history. Without carvings or decorations to draw attention, the tablet became invisible in plain sight. Yet hidden in its silent numbers was a story waiting to erupt, a story powerful enough to challenge everything we thought we knew about the origins of mathematics. Forgotten for decades, once Plimpton 322 entered Columbia University's archives, it slipped into obscurity. Labeled with a catalog number and stored with other Mesopotamian artifacts, it became just another item in a vast collection. Scholars occasionally glanced at it, but few lingered. To most, it was assumed to be a mundane record, perhaps of food rations, temple offerings, or lists of trade goods. Its plain surface and lack of decoration offered no clue that it held anything of value. And so, while great discoveries were being celebrated across the world, ancient tombs uncovered in Egypt, lost cities mapped in Central America, this small slab of clay simply gathered dust. It was there through 2 world wars, through the rise and fall of empires, and through the rapid growth of modern science. Decade after decade passed, yet the tablet remained silent, overlooked by those who believed they already knew the limits of Babylonian mathematics. A few specialists did notice its odd structure, the neat rows and columns that hinted at hidden order, but without modern tools, the meaning stayed locked away. For nearly a century, Plimpton 322 sat forgotten, its secret knowledge invisible to all who passed it by. It was a relic ignored, patiently waiting for the right moment in history, when technology would finally catch up to what ancient scribes had etched into its fragile clay. Scholars noticed patterns in the mid-20th century. A few curious minds began to look closer at Plimpton 322. Unlike most who dismissed it as an inventory list, these scholars noticed something unusual. The arrangement of numbers wasn't random. It followed a strange rhythm. In the 1940s, mathematicians studying the cuneiform symbols realized the values carved into the clay seemed connected to right-angled triangles. Some even suggested the Babylonians might have been working with what we now call Pythagorean triples, whole numbers that perfectly describe the sides of a right triangle. But the tablet was damaged, with pieces missing and erosion obscuring parts of the rows. Without the full picture, the numbers felt incomplete, like a puzzle with missing pieces. To some, it was nothing more than coincidence. To others, it hinted at something far deeper. Still, without solid evidence, the academic world remained divided. Was it simply a table of exercises for training scribes? Or was it proof that the Babylonians had mastered mathematical ideas long before the Greeks? For decades, the debate lingered quietly in specialist circles, fascinating a handful of historians and mathematicians but ignored by the wider world. The clues were there, etched in ancient clay, but the tablet's true purpose stayed hidden, waiting for modern tools to reveal its astonishing message. Still a mystery despite the hints uncovered by a few mathematicians, Plimpton 322 remained stubbornly silent. Its neat columns of numbers fascinated specialists, but no one could agree on their meaning. Some thought it was a teacher's aid, a kind of classroom exercise in mathematics. Others suggested it might have been a list of problems, or perhaps a table to help with routine accounting. Yet none of these ideas fully explained its precision or structure. Entire rows were missing due to erosion, leaving the sequence incomplete, like a story torn in half. Without those missing pieces, the logic behind the tablet stayed hidden. Scholars published papers, debated theories, and quietly set it aside again. For most of the 20th century, the artifact was treated as an oddity, intriguing, but ultimately unsolved. To the general public, it was virtually unknown. The spotlight of history shone elsewhere, on dramatic discoveries like Tutankhamun's tomb or the Dead Sea Scrolls. Meanwhile, Plimpton 322 sat in quiet obscurity, a cracked clay fragment no one could fully decipher. It was a puzzle without enough clues, a mystery too fragile to solve with the tools of the time. Decade after decade, the slab waited, its secret hidden in plain sight, until technology finally advanced enough to bring its true voice to life. AI enters the story. The mystery of Plimpton 322 might have remained unsolved forever, if not for a surprising twist in the modern age. Thousands of miles from Babylon in Australia, mathematician Daniel Mansfield stumbled across a photograph of the tablet while working on a project for high school teachers. Something about the image refused to leave his mind. The numbers weren't chaotic. They carried balance, rhythm, and intention. Mansfield suspected there was a hidden system at work, something far more advanced than scholars had ever suggested. But he also knew human intuition alone could not unlock it. So he teamed up with fellow researcher Norman Wildberger at the University of New South Wales, and together they turned to a new kind of tool, artificial intelligence. They fed the tablet's surviving data into machine learning models trained on Babylonian mathematics and cuneiform writing. The AI compared the damaged rows with thousands of other tablets, studying the way ancient scribes recorded numbers and solved problems. Slowly, it began filling in the missing pieces, reconstructing what erosion had erased. What had been a broken puzzle started to take shape again, and when the final patterns emerged, the results stunned even the experts. The silence of Plimpton 322 was broken, not by chance, but by the power of modern machines listening to voices from nearly 4,000 years ago, filling the missing rows as the algorithms worked through the fragmented lines of Plimpton 322. Something extraordinary began to emerge. Where erosion had left empty spaces, the AI generated likely reconstructions, comparing them against patterns from other Babylonian texts. Slowly, the gaps that had silenced the tablet for centuries began to close. What had once been a jagged puzzle of broken symbols was transformed into a complete, coherent sequence. Row by row, the numbers aligned with precision, forming patterns that were impossible to ignore. This wasn't random bookkeeping. It wasn't a list of rations or temple offerings. The reconstructed tablet showed deliberate, structured mathematics. The numbers fit together as if following an invisible set of rules, each row flowing logically into the next. For the first time since it was carved nearly 4,000 years ago, Plimpton 322 spoke in full sentences instead of fragments. And its voice was clear. This was not an accident. The Babylonians had carefully built a table of numbers with intention, consistency, and accuracy that rivaled modern methods. What the AI revealed went beyond restoring symbols in clay. It restored a lost piece of human thought. A tablet once seen as broken and meaningless had transformed into a guide, a window into knowledge that defied history's timeline. A tool, not records. When the reconstruction was complete, scholars realized Plimpton 322 was not a dull record of goods or offerings at all. It was a tool. The numbers weren't random entries, they were organized with intention, forming a mathematical table. Each row followed a pattern, precise and consistent, pointing to a deeper purpose. Far from being a simple ledger, this clay slab looked more like a reference book, something designed to be used. It was as if ancient scribes had carved a calculator into clay. The discovery overturned long-held assumptions about Babylonian knowledge. This was not basic arithmetic or bookkeeping. It was higher mathematics, developed thousands of years earlier than anyone believed possible. The neat rows of cuneiform weren't notes for training or scribal practice. They were functional, practical, and accurate, meant to solve problems in the real world. The realization was staggering. A tablet once ignored as mundane had revealed itself to be evidence of a sophisticated mathematical system. It wasn't myth, it wasn't coincidence, it was deliberate science. Plimpton 322 was a tool of power and precision crafted in an age we thought too early for such ideas. Its existence forced scholars to admit a humbling truth: history had underestimated Babylon. Math before the Greeks for centuries. School books have credited the Greeks with creating trigonometry, pointing to Pythagoras and his famous theorem as the beginning of advanced geometry. But the numbers on Plimpton 322 challenged that story in a dramatic way. When researchers analyzed the reconstructed tablet, they realized the Babylonians had discovered the same mathematical truths more than 1,000 years before Pythagoras was even born. The rows on the clay slab contained what modern mathematicians call Pythagorean triples, sets of whole numbers that perfectly describe the sides of a right-angled triangle. This meant that long before Greek philosophers debated shapes and proofs, Babylonian scribes were already working with these relationships, recording them in exact sequences. The idea that trigonometry began in Greece suddenly collapsed. Instead, it appeared the Babylonians had laid the foundation centuries earlier, and possibly in a way even more refined. What had once been dismissed as primitive suddenly stood revealed as pioneering. Plimpton 322 wasn't just an artifact. It was proof that human knowledge doesn't always follow the clean timeline we were taught. The Greeks may have popularized geometry, but the Babylonians had mastered it first, etching their genius into clay while history forgot to give them credit. The triple numbers, when scholars looked closer at the sequences carved into Plimpton 322, they realized the Babylonians were working with something astonishing: Pythagorean triples. These are sets of 3 whole numbers, like 3, 4, 5, that perfectly fit the rule of right-angled triangles, where the square of the longest side equals the sum of the squares of the other two. In today's classrooms, that rule is written as a plebiscitaus, but on this ancient clay slab, the relationships were preserved in the Babylonians' base 60 numbering system centuries before Pythagoras lived. Each row of the tablet contained a new triple, carefully arranged in order, not scattered by chance. This wasn't a random discovery. It was a deliberate catalog of mathematical truths. More than 1 or 2 examples, the tablet held a series showing that Babylonian scribes understood the pattern deeply and systematically. They weren't just experimenting. They were building a tool, a guide to right triangles that could be applied to real-world problems. The realization shocked historians. The Babylonians weren't stumbling into mathematics. They were structuring it with accuracy and foresight. The triple numbers etched into Plimpton 322 became undeniable proof of a civilization working at a level far beyond what history had assumed. Ratios, not angles. As Mansfield and Wildberger studied the completed reconstruction, they discovered something even more surprising than the triples themselves. The Babylonians were not thinking in terms of angles at all. Modern trigonometry is built on sines, cosines, and tangents, functions that depend on measuring degrees. But degrees require specialized tools, and they also introduce approximation, especially when irrational numbers are involved. The Babylonians solved this problem in a completely different way. Instead of measuring the angle of a slope, they measured the exact ratio between the sides of a triangle. Every entry on Plimpton 322 reflected this approach, whole number proportions expressed in their base 60 system. This method didn't create rounding errors or approximations. It delivered pure accuracy. The brilliance of this approach was its simplicity. By focusing on ratios, they could scale triangles to any size without losing precision. A surveyor planning a field, a builder raising a temple, or an engineer digging a canal could all rely on this system to achieve perfect results. It was a fundamentally different vision of trigonometry, one uniquely their own. Instead of being behind the Greeks, the Babylonians had developed a practical method that in some ways was more powerful than the one we use today. Perfect accuracy, one of the most striking features of the Babylonian system, was its precision. Modern trigonometry, built on Greek methods, often relies on approximations when dealing with irrational numbers. Angles and decimal points can never be measured with complete perfection, and rounding errors slip in. But the Babylonians avoided this problem entirely. By using exact ratios and their base 60 numbering system, they worked only with whole numbers and fractions that fit neatly into their mathematics. The result was calculations that were flawless, free from the small errors that creep into modern methods. Imagine being a builder in ancient Babylon, planning a massive temple or canal. With this system, you could create perfectly straight walls, exact corners, and precise slopes, all without the need for measuring degrees. The tablet was not just theoretical knowledge, it was a practical guide to achieve mathematical certainty in the real world. No guesswork, no approximations, just numbers that aligned with absolute consistency. This level of accuracy, carved into clay almost 4,000 years ago, shocked modern experts. It suggested that the Babylonians weren't just experimenting with ideas. They had mastered a system of mathematics designed to deliver results with a clarity and precision that rival, and in some cases surpass, the techniques we rely on today. Power for builders. The practical strength of the Babylonian method became clear when researchers imagined how it was used. In a world without compasses, protractors, or advanced measuring tools, angles were difficult to work with, but ratios, simple whole number relationships, were easy to record, scale, and apply. A surveyor planning farmland could use these ratios to mark out perfectly square plots. An architect designing a temple could ensure each corner was exact, the walls aligned with flawless precision. Engineers digging irrigation canals could calculate slopes so water flowed smoothly across great distances. All of this could be done using the proportions carved into Plimpton 322, without ever measuring a degree. It was a system tailor-made for real life, practical and elegant. Imagine building vast ziggurats that touched the skies, or plotting the borders of land in disputes. Ratios gave Babylonians the power to shape their world with mathematical certainty. Modern scholars realized that this wasn't abstract knowledge tucked away in temples, it was a working toolkit for society. Through these numbers, the Babylonians mastered control over space, design, and infrastructure. The tablet's hidden purpose was clear. It armed builders and engineers with the precision to create monuments and systems that stood the test of time. More than geometry, Plimpton 322 proved the Babylonians were not simply solving classroom puzzles or drawing neat triangles for practice. Their mathematics went beyond geometry. It was woven into the fabric of daily life and governance. This knowledge was practical, powerful, and deeply tied to the way society functioned. If a tablet like Plimpton 322 could provide exact ratios for constructing right angles, then it wasn't only about temples or canals, it was about control. Land was measured and divided, ownership decided, and disputes settled with the authority of mathematics. Numbers weren't just symbols in clay, they were tools of order, fairness, and sometimes power. The Babylonians had taken abstract relationships between numbers and turned them into a working system that touched everything from farming to architecture to law. And unlike the Greek focus on theory and proofs, this system was rooted in application. It wasn't knowledge for its own sake. It was knowledge meant to be used, to see mathematics expressed not as abstract formulas, but as a guide for living reshaped how historians thought about the past. This was not primitive thought. It was advanced reasoning, centuries ahead of its supposed time, showing that Babylon's genius was both intellectual and practical. The surveyors mapped the true reach of Babylonian mathematics became clearer with another artifact, a tablet known as C.427. Unlike Plimpton 322, this slab wasn't filled with endless columns of numbers. Instead, it carried a diagram, a kind of map. Straight lines, careful measurements, and notations etched into the clay revealed what looked astonishingly modern, a surveying plan. Dating back almost 700 years, C.427 was created not for a temple or royal archive, but for something deeply human, a legal dispute over farmland. This was math at work in society, used to settle who owned which piece of land. The map wasn't a rough sketch. It showed right angles, measured boundaries, and an understanding of geometric relationships that matched the exact precision suggested by Plimpton 322. Together, the two tablets formed a pair, one holding the mathematical formulas, the other showing those formulas in action. A surveyor, armed with ratios from Plimpton 322, could divide fields with fairness and accuracy, drawing borders that carried authority. This was no longer just abstract mathematics, it was a system shaping real lives. The discovery of C.427 proved the Babylonians weren't only recording knowledge. They were applying it to law, property, and governance centuries ahead of what history had credited them for. Math as authority. The discovery of C.427 revealed something unsettling. Mathematics in Babylon wasn't only about building temples or digging canals. It was about power. By using ratios and geometry to measure land with precision, Babylonian authorities could decide who owned what, where boundaries were drawn, and how resources like water flowed. In a world where survival depended on fertile fields and irrigation, those decisions shaped lives. Math became more than a tool of science. It became a framework of authority. Whoever held this knowledge held control. A clay tablet could settle disputes, enforce fairness, or secure dominance, depending on who wielded it. Imagine standing in front of a Babylonian judge, your future decided not by argument, but by the cold certainty of numbers etched into clay. This wasn't abstract theory hidden in libraries. It was living law, carried out in fields, roads, and canals. What feels modern today, cadastral maps, GPS boundaries, legal surveys, had already begun thousands of years ago in Babylon. Math was their instrument of order, their guarantee of fairness, and their claim to power.